Last episode, we ran the whole loop in one sitting: load data, build a model, fit, evaluate. And it just worked. But did you notice the cheat? We loaded the entire dataset into memory with one line. That's fine for a toy. The moment your data is bigger than RAM, thousands of images sitting on disk, that one line falls apart. This episode lives in the same place on our pipeline spine: collect and pre-process. But this time we go deep on the part nobody warns you about: how the data actually gets to your model batch after batch without ever making your GPU wait. Here's the trap. In episode 2, the whole dataset fit in a NumPy array and Keras was happy. Real datasets don't fit. A folder of 100,000 photos is 40 gigabytes. You can't hold that in memory, and you definitely can't pass it as one array. So the question becomes, how do you stream it piece by piece, fast enough that training never stalls? And training does stall. People spend thousands on a fast GPU, start a training run, and watch it crawl. They blame the model. It's almost never the model. It's the GPU sitting idle, twiddling its thumbs, waiting for the next batch to be read off a slow disk and decoded. A race car stuck behind a tractor. The compute is fast, the feeding is slow. That's the bottleneck. tf.data fixes this by being lazy, and I mean that as a compliment. A tf.data dataset is not your data. It's a recipe for your data, a conveyor belt of instructions. Nothing is read, nothing is decoded, nothing happens at all until the model actually asks for a batch. You describe the pipeline once, it runs on demand forever. The first instruction on the belt is map. You give it a function. Here we scale each feature row by dividing it by its own largest value. So the biggest entry becomes 1 and the rest fall in proportion. And map applies it to every element as it flows past. The magic word is auto-tune. Instead of you guessing how many CPU workers should run that function in parallel, auto-tune measures your machine at runtime and picks the number for you. Set it and forget it. Next, cache. The first epoch, your data gets read and mapped. That's expensive. But epoch 2 through 50, it's the same data. So cache says, read it and process it once, then keep the result in RAM. Every later epoch reads from memory at the speed of light instead of redoing the work. One line, enormous payoff. Then shuffle, and here's where order bites people. If your folder has all the cats first and all the dogs second, and you don't shuffle, the model sees 1,000 cats, then 1,000 dogs, and it learns garbage. Shuffle fixes it, but the buffer size matters. Shuffle 1000 keeps 1,000 items in a pool and draws randomly. Too small a buffer and the randomness is fake. You'll still see local patterns leak through. Big enough to actually mix is the rule. And notice the order. We cache before we shuffle. So the expensive read happens once, but the shuffle still reshuffles fresh every epoch because it sits downstream of the cache. Then batch group the shuffled stream into chunks of 32 because the GPU wants a stack, not one example at a time. And finally, the move that wins the whole race, prefetch. While the GPU is chewing on batch number 5, prefetch is already reading and prepping batch 6 in the background. Compute and data loading happen at the same time instead of taking turns. That overlap is the difference between a 19-second epoch and a 6-second one. One more gift. For images, you don't even have to write the loader. Image dataset from directory. You point it at a folder where each subfolder is a class, like daisy, roses, and tulips, and it hands you a ready-made dataset with the labels inferred for free, resized, batched, done. So that's the data sorted, collected, cleaned, streaming fast, which leaves the obvious next question. What exactly is this model we keep feeding? Time to open it up, the neuron. Let's build the pipeline in code. 2 short pages. Page 1 is the in-memory pipeline, the full chain of operators on a small array, so you can see each link. Page 2 is the real-world version, loading images straight from folders, same ideas scaled up. top of the file, import TensorFlow, grab Keras, and pull autotune out of tf.data. That constant is the one we'll hand to map and prefetch, so TensorFlow tunes parallelism for us. Some toy data, a small array of fake feature vectors and their labels, and from tensor slices, this is the entry ramp. It turns arrays into a dataset, slicing along the first axis so each element is one example paired with one label. A normalize function, it scales a single feature row by dividing it by that row's maximum value. So every row lands on a common 0 to 1 footing, and we map it across the dataset with num parallel calls autotune. Notice the function operates on one element at a time. tf.data handles fanning it out across cores. Now the chain that does the real work, cache, then shuffle 1000, then batch 32, then prefetch autotune. Order is deliberate. Cache before shuffle, so the expensive read happens once. Shuffle before batch, so each batch is a fresh random mix. Prefetch last, so it stages the finished batches. Print the dataset and you see its element spec. The shape contract, because prefetch is the last op, what prints is a prefetch dataset. And we iterate exactly one batch with a for loop and break, printing the feature and label shapes. 32 rows. Proof the belt is delivering stacks, not single items. Page 2, the real thing. Image dataset from directory pointed at a flowers folder. Image size 180 by 180, batch 32. It walks the subfolders, infers the class names, and gives back a batched labeled dataset. We grab the class names of it for later. Now the image normalization, and here the divide by 255 actually belongs because raw image pixels really do run 0 to 255. A rescaling 1 or 255 layer folded into a map, then cache and prefetch. We skip from tensor slices here because image dataset from directory already returns a dataset. And we take one to preview a single batch, printing its shape, 32 images, 180 by 180, 3 color channels, and the matching labels. That's a production grade input pipeline in under 30 lines. Lazy, parallel, cached, shuffled, prefetched. Your GPU never starves. We've now collected and preprocessed our data properly. The front half of the pipeline spine is solid. Next episode, we finally crack open the box we keep feeding. The neuron, the layer, the network, building an artificial neural network by hand from a single unit up.